Hello and welcome to Innovation Celebration, the show where we celebrate recent advancements in science and technology, the people and ideas that make those possible, and the ways in which they enhance human flourishing. I'm Thomas Walker.
And I'm Angelica Worth.
And today we want to talk about another topic that we'll spend the whole episode dealing with, and this week we want to focus on robotics. Now when we talk about robotics, really what we're talking about is computer-controlled machines that have a degree of independent movement and are able to operate somewhat autonomously to various degrees. Now there's a history that comes before that of how that movement capability was developed before computer or electronic control existed. So I will hand over to you about that in a moment. But before I mention that, just a note on the word robot, which actually came from a Czech playwright named Karel Čapek. In 1921, he released a play called, Rossum's Universal Robot. Robot there was a Czech word for forced labour. So interestingly, that idea of being a servitor is in there from the start. But do you want to take us through some of those early sort of pre-electrical?
Yeah. And so these are not what we think of as robots in the sense that they're not electronic, they're not computer controlled, and they could usually really only do a couple of things. But it's important to consider them when we're talking about the history of robots because it's how objects moved on their own, in the early days. So it's useful for understanding the history of how the motion developed. And so this goes all the way back to like ancient Egypt and ancient Greece. For example, in ancient Egypt, they had these clocks called water clocks. Well, they're called clepsydra, but water clocks that you'd have one bowl of water and another bowl of water, and the water would flow from one into the other, kind of like an hourglass. So when the water had flowed from one to the other, a certain amount of time had passed. And so the step up from that was that the ancient Egyptians figured out how to, when that happened, make a little figurine hit a bell or a gong or something.
So kind of like a modern cuckoo clock.
Yeah, rather like a cuckoo clock. And you mostly just had things like that, little figurines that could do one task and one task only, for centuries really, until you had the Spanish engineer Giovanni Torriani come along in the he was making robots mostly in 1550s, 1560s time frame. And so popular wisdom on the internet has it that in 1557 he developed a wooden robot that could deliver the emperor's daily bread. I could not find any specifications of how this robot actually worked. Was it a wind-up thing? Could it just go in a straight line? Like, what were its limitations? What was its design? I couldn't find any of that. However, there was another design that Torriani did around the same time. That's a little wind-up thing that just kind of walks around in a circle and moves its arms, and that we actually do have this figurine still. Not me personally, it's in the Smithsonian.
It still works?
It still works. It's just a wind-up thing, and so you can just wind it up and it'll do its little walk around and move its arms thing.
Cool.
So it moves its mouth, but it doesn't make sound. So that's in the Smithsonian. That's a thing that still functions. So I imagine this bread-fetching robot worked similarly. Other inventors of note in, I think it was the 1600s, you had Jacques de Vaucanson, who developed a number of robots for different purposes. My favorite are automata. They're not really robots. My favorite was the one who could play 12 different songs on a flute. You didn't have radio yet, or records or anything. In the 1800s, you had Thomas Edison, who developed a talking doll. Really, it's a precursor to those things that most parents hate because they make noise, the little toys that talk to you, but they just have a certain number of pre-recorded messages. In the case of Edison's doll, it actually just knew one nursery rhyme. But they're kind of nightmarish, really, in my opinion, because they're not like nice, cuddly dolls that you want to play with. They're like nice dolls, and then on their chest there's this big metal speaker.
Oh, because I'm picturing like a Teletubby with the screen on the belly.
Yeah, it's kind of like that. It like has holes in it too, like a shower drain or something. I don't know. It looks kind of bad in my opinion.
You have to go through these stages in the
You do, yeah. And then around the same time, you also had the Canadians develop steam-powered robots, or automata.
I love the idea of a robot walking along with just a chimney on the top and
to
smoke coming
steam,
out.
Right? Yeah. But yeah, things really started to get interesting after what you were talking about in the 1920s, where robot, the word really came along, and
Yeah, so I think the real sort of start of electronic robots or electronic control that led to robotics was Tesla's teleautomaton.
Nikola Tesla.
Sorry, teleautomaton. I keep saying that wrong every time. Yeah, this is not Elon Musk Tesla. This is Nikola Tesla, after whom that company is named. But he developed what nowadays would sort of come across to us as a radio-controlled boat. Like the sort of model boats that people drive around on lakes.
Sure.
But this was the first use of radio control as a way of controlling an electronic object. And he actually invented basically what's nowadays known as a logic gate, as in a system where you have two inputs, and depending on the nature of the two inputs, it puts out one output. So OR gates, if you have a one yes, one no, it puts out a yes. AND gates, you have to have both positive to put out a positive, and NOR, or there's several different kinds, and you can string those together to make more complicated processing. But this was the first time something like that had been developed in order to convert what he called Hertzian waves, i.e. radio waves, into the boat's sort of instructions. But he didn't release that technology at the time. He kept it secret because he was worried about people stealing his invention. And I have a little quote from Tesla I want to read out, just because he clearly had a longer term vision in mind for this. And even though it's basically just a remote controlled boat, he says, "I treated the whole field broadly, not limiting myself to mechanisms controlled from a distance, but to machines possessed of their own intelligence. Since that time, I had advanced greatly in the evolution of the invention, and think that the time is not distant where I shall show an automaton which, left to itself, will act as though possessed of reason and without any willful control from the outside. Whatever be the practical possibilities of such an achievement, it will mark the beginning of a new epoch in mechanics." Now,
man with a vision.
Yeah, a little ahead of his time. In fact, even ahead of our time, really, in some of what he's saying there. But nevertheless, clearly had an idea of where that technology might take us.
Yeah.
And so definitely, somebody worth celebrating.
Absolutely. And in fact, our colleagues did celebrate it over at the Hero Show. They did an episode on Nikola Tesla and George Westinghouse, who actually also did something with robotics, didn't he?
Yes, I'm going to come to that in a minute.
That's later, okay.
And then, so after that, the sort of next big step that I want to bring up is Electro the Moto Man.
Can tell this is a name from the 30s, right?
It's the 1939 World's Fair that this was announced at, and this is actually the Westinghouse company. So, as I say, on that same episode of the Hero Show, they talk about Tesla and Westinghouse. This is his company. Built this giant metal humanoid robot. If anyone's seen the movie, the name's slipped my mind now. The Day the Earth Stood Still, 1950s version of The Day the Earth Stood Still. There's a robot called Gort, this gigantic steel menacing robot. And Electro the Motor Man looks like that. It's just this huge iron giant kind of thing.
Like.
Yeah, but it also had a vinyl record player inside it. So the advertisement was that it can respond to spoken commands and speak back to you. What it was actually doing is, if you spoke the command at the proper intonation, you had to hit the right syllables at the right times, and it actually converted that into a series of electrical impulses that it then turned into a flashing light that then told the vinyl record player which recording to play back.
Sure.
So if you spoke the instructions correctly, you could actually speak anything really, as long as you made the right intonations at the right points. So, very early, but it was really just a way of showing off Westinghouse's technologies and sort of attracting business for the company.
A very early version of Siri, almost.
Yeah, but it was actually based on the Televox. Sorry, it's based on the Televox. I've left my notes too far away for me to actually read them. It was actually based on the Televox, which is Westinghouse's system for switching in electrical substations.
So that's a good example of how developments in different fields added to robotics and vice versa. We'll come to some examples in a bit where advancements in robotics have helped with other fields.
Yeah, but I just wanted to read out the quite funny line that Electro would read out to his audiences. He would say, "Ladies and gentlemen, I'll be very glad to tell my story. I am a smart fellow, as I have a very fine brain of 48 electrical relays."
48 whole relays.
So, I just thought that was a wonderful example of where the technology was at the time.
Yeah. So then moving along in the decades following that, you obviously had the development of computers going on, and you had some interesting developments in the field of robotics. So one thing that a lot of us think about when we think about robotics helping us do work and helping us with productivity is robots that work on assembly lines, like with cars and things. And so the first significant robot like that was called Unimate, which stands for Universal Automation. It was developed by a rather shy inventor named George Devil in the late 1950s. They finally got it patented in 1961, but with the help of a businessman, Joseph Engelberger, they actually managed to sell it before then to General Motors, and I believe it was 1959. And so what General Motors used it for was die casting, which is a part of making cars that involves a lot of toxic fumes and molten metal, so it's really dangerous, which makes it a really good candidate for, but it's also just the same thing over and over again, which makes it a great candidate for bringing in robots, because then you're not exposing people to that risk. And then around that same time, at Stanford in 1958, you had the development of a robot called Shaky. The team there was led by a man named Charles Rosen, and Shaky could roll around the room, he could shake hands with people, he could talk in a limited way. I think it was similar to Electro the Moto Man, where certain things would spark certain responses. And though he rolled around the room, he didn't do it very well. He was very unstable. That's why they named him Shaky, because he shook. But it was an advancement toward humanoid robots. It wasn't really a humanoid robot yet, but we're getting there. And not long after that, I think, or in that same time frame too, we also had robots helping with science.
Well, so what I wanted to talk about just at this point in the historical story, although it's kind of tangential, is robotic spacecraft. So when the space program starts in not the space program, but when orbital spaceflight starts in the late 1950s, both of the two countries doing it, the USSR and the USA, were launching initially satellites and then deep space probes that really had very little to no control over their movement. They were just launched on ballistic trajectories. So you'd aim the rocket and then sort of hope it carries on in that direction, which obviously objects in space generally keep going in the same direction, but unless something acts on them. So the very first deep space exploration was sending probes to the moon, but these were impactors. They were basically just a metal ball full of sensors and instruments that were transmitting data back to Earth, but they were just on a trajectory to crash into the surface of the moon. And that was the first way of sort of learning about the moon in detail. Funnily enough, actually, one of the Russian lunar probes, Luna, Luna, missed the moon, and the Soviets, in typical fashion, pretended that was the plan all along, and triumphantly announced that they had launched the first ever artificial object into orbit around the sun, because it flew straight past the moon and off out into interplanetary space.
I mean, they did. That's just not what they intended to do.
It was an achievement in a sense, but by complete accident. But clearly they needed more control if they were both sides wanted to do manned missions to the moon. So and they needed to send probes ahead of time to learn about the characteristics. At that point, what kind of environment was on the surface just wasn't clear. So they started to develop what's called telerobotics, which is the ability of probes to move with themselves and position themselves remotely. The thing is with space is you have such large distances, and the moon is 2.5 seconds away, so it's not that big a deal at the speed of light. So is a bit of a lag for your instructions if you're going to try and control something remotely to get there. When in the late 60s, early 70s, when they're starting to send probes to Mars and Venus, you've got 20-minute delays on signals getting there, or more, depending where the planets are in their orbits. So to be able to do that and do orbital insertion to catch up to a moving planet and then settle down into orbit around it, has to be able to do it by itself, really, without direct control.
Well, and with Mars exploration, yes, isn't there a point where we can't communicate with Mars at all?
Yeah, so that's actually any planet really is at some point in its orbit going to be on the opposite side of the sun from us.
Right.
With the planets further out, that's less frequently, but the inner planets more frequently. And so there's entire periods where you have no real you can't communicate through the sun. So but in the 1970s as well, NASA did the Viking landers on Mars, and the Russians did the Varena landers on Venus, and both of those needed to be able to deal with the process of landing through an atmosphere with winds. On Venus it's worse with lightning and things like that going on, and it needs to be able to respond to all these sudden unexpected conditions. And so developing planetary landers that can basically land themselves remotely was an important step. And then sort of going more further forward than that, in the 1990s you had the Cassini-Huygens mission, which was to Saturn. But the Huygens lander had to, and Saturn is 10-12 hours signal time.
Pretty far,
That's a real enormous distance. So it needed to be able to, and the Huygens was landing on Titan, another body with a very thick atmosphere. It had to be able to deal with winds and the possibility of landing in a lake and all these sorts of things. So that had to conduct itself completely autonomously. Everyone was just sitting at the Jet Propulsion Laboratory waiting for to find out if it had done it or not, because they couldn't do anything to help. And likewise, Cassini, during its mission, did a number of dives through Saturn's ring system. And the rings of Saturn are made up of lumps of ice, dust, and rock, just in this enormous, gigantic plane full of junk, flying in all different directions. And you're diving through that, taking readings, needing to be able to dodge anything that comes flying at you when you're, half a day away from communications.
Yeah.
It's just, so that it had to have that higher level. And then when we talk a bit about applications later, I'll actually get more into some more recent spacecraft and how they've used robotics in more interesting ways. But that was the sort of, right back into the 1960s, they had to be able to do it to some extent.
Cool. Well, moving on into the 70s, then you also have this process of refining the movements of the robots so that they can be more precise and do more things. So two big examples of that I'll start with. We've got Wabbot 1.
Wabot,
sorry. WABOT 1, which was developed at a Japanese university called Waseda University. There was also a Wabbot 2 that could play the piano, but that's all it could do. It just played the piano. So Wabbot 1, which was finished or announced in 1973, could also, like some of the earlier robots we were talking about, could wave at people, could shake hands, had some amount of speech that it would reply with. I couldn't find whether it was pre-recorded or whether it was synthesizing words or not. So I'm not sure where it stands on that, but it was talking in Japanese because it was a Japanese university that made it, but one of its big upgrades as compared to Shaky is that it was more humanoid. In fact, a lot of people call it the first bipedal humanoid robot because it was much closer to human shape and it did walk on 2 feet.
Right.
It was just really slow. It took
it's ridiculously difficult to balance something on 2 legs.
Yeah, so the solution with Wabbot was just, we'll just do it really slow so we can get everything right.
Yeah.
So it took 45 seconds to take one step.
Just
one single step.
the balance involved in standing on 2
it's
legs.
enormous. Yeah, so this was a move towards things and it just was slow, that's all.
Yeah.
And then you had in the same year Famulus, which was sort of a step up from...
Sounds like a Roman person, yeah.
Well, it was developed by Germans, actually.
Oh, okay.
By a German company called KUKA Robotics, which still exists today, but it's owned by the Chinese Medea Group. It was acquired by them in 2016. But Famulus was sort of like Unimate in that it was meant to work on assembly lines and in industrial operations. But it was significant because it had a lot more articulation than earlier robots. It just could move in more ways and in different directions and do things, do more things, basically. So that was why that was notable. And then following along in 1975, you had a Swedish company called ASEA that developed the IRB6, which was notable because it was the first one to be controlled by a computer chip. In this case, it was actually the Intel. I think it's a microchip by then, in 75. Yeah. So Intel's microchip, one of their first, was used to control IRB6, which was developed and manufactured by ASEA. And then the other thing to note when we're talking about robotics and computers is that in the 70s they were starting to develop programming languages that really worked, for programming robots and computers. So, and some of those are still functional today, although they're not commonly used. So most notably you have the programming language POP2, which was used to program Freddy 2. Nothing to do with the movie.
Because if you Google that, you get a lot of Nightmare on Elm Street 2 pictures there.
But Freddy 2 wasn't even humanoid. He was like a trapezoid with, arms. It was very strange. They called it Freddy, but more importantly to note here, POP 2 is the language for Freddy 2 the robot. Both of those were 2s because they were both second iterations.
Yeah.
Things tend to take time to work correctly. First iterations of POP and Freddy didn't work as they were supposed to.
Well, you'll see the same in what I want to talk about next, which is really sort of a successor to Wabbit, because it's another Japanese human form robotics development. And when I was young, which is a long time ago now, I read a lot of books on robots and all sorts of scientific subjects really. And at the time, the new thing on the block was the Honda P3, and Honda actually, as they say, P3. They made 4 P series robots, and so Honda consider their mission as a company to be improving mobility. They're a car and motorcycle manufacturer, but they actually make jets now as well. They've recently moved into that business. But their thinking was, some people have mobility issues at home. Maybe we can use our automotive technologies to address that area of mobility as well.
Sure, yeah.
So they started this development program of creating what would be household servant robots for people with restricted mobility. Sure. And I'd say the P1 was their first attempt, which is very blocky, kind of exposed mechanics kind of thing. But by the time it got to P3, the P3 looked like an astronaut. It had this kind of helmet and a backpack with all its gear in, and it could walk downstairs. It could balance. If you could push it and it would somewhat be able to adjust its balance back. So it's a progression of that.
And just think how helpful that would be for somebody who really struggles to go up and down stairs if they could send a robot to get something or do something.
Yeah, totally. And so the P3 had the ability. It was also the first one that could respond to voice commands. The P1 and the P2, you had to type into a PC to tell it what to do, but the P3 could answer voice commands. And then sort of moving forward, this was in the late 80s, early 90s, and then moving forward into 2000, Honda progressed to Asimo, which is kind of the P5, but they decided to give it the name Asimo, which is a anagram for... Not anagram. What do I mean?
Portmanteau.
It is an anagram for advanced step in innovative mobility, but also... Not an anagram. What do I mean? Acronym. It's an acronym for Advanced Step in Innovative Mobility. It's also a portmanteau of ASI in Japanese, meaning leg, and then Mo meaning mobility. And it's almost certainly a reference to Isaac Asimov, the iRobot author as well.
Yeah, we've mentioned on the show once or twice before how fiction can influence and inspire technological innovations, and here's another example.
Yeah, and Asimo is like a smaller, more nimble form of the P3, P4 design, and could run. It can recognize faces and name them, up to 10 different faces. It knows its own name. It can respond to calls.
Like a dog.
Yeah, if you want a dog, just get a dog. But this is if you need a servant around the house. But it could also determine the distances and directions of objects in its environment. It can hear sounds and know what they are. Some certain sounds, like something being dropped. If you're in old ladies in the kitchen and drops a glass or something, it will know to come and help. So there's a lot of progression on those sorts of things, and much better in the balance realm. And they kept developing that right the way up to 2018, and they sort of discontinued the program at that point. They're still doing humanoid robot research. They just discontinued Asimo, but they at that point said, we've developed technologies here that we can put back into our other fields, and so a lot of that stuff's now gone into their car design. Parking sensors, so auto drive systems, text to speech, voice control systems for their cars.
Sure, yeah.
Meanwhile, the mantle's been picked up somewhat by Boston Dynamics, who spun out of MIT in 1992, sort of became an independent company, and but shot to fame more recently for a number of their products. They're not Mad Dog. What is it?
Spot.
Not Spot. The bigger dog. They have a Big Dog. Okay.
That's creative. Big Dog.
Big Dog is their sort of main product that's currently commercially available. That was created as a pack mule for the army. So it's kind of like a mule would be, like it carries equipment around. But the army said it's too noisy, so they just released it into commercial applications. And you started to see them quite a lot. And then they have a smaller version of that called Spot, which we've actually
We
seen.
saw it in person, yeah.
Because we were in a hotel in Boston a couple of months ago, and one of them just happened to be there on display. Well, it was on display.
I think they were trying to sell it to somebody.
It was a group of guys in the canteen just
Yeah.
had it there, yeah. But I'll talk actually a bit later about one of the applications that Spot's currently being put to use with. And then there's Cheetah, which is this faster version of the canine dog thing, and the dog
Even
design.
though cheetahs aren't canines.
They are indeed cats, but that's besides the point. But the thing that goes back to my point that bipedal motion is really difficult.
Right, so they just said, let's not do that, let's do forelegs instead.
Yeah, quadrupedal design is just inherently more stable, really.
Mm-hmm.
And then, but they do also have a bipedal, which is called Atlas, which can do parkour.
Which you've mentioned on the show before, I think.
Yeah, we talked before, and you may have seen videos of it doing military training, which are actually visual effects videos.
Yeah, they're not doing that.
I know the company that made those; they're really cool. But it does have really impressive capabilities. It can run, jump, get pushed over, get back up.
Yeah.
So there's some quite cool developments in that direction. But the dog bots are sort of their focus for the time being commercially.
Sure, yeah. Yeah, so we wanted to talk a little bit more, take a break from talking about the progression of robots and talk about how they actually work just a little bit. It gets kind of complicated, but we want to talk about some of the basic elements that you need. And so the first one you need is robots have to be able to sense their environment to some extent. Even if that's just your Roomba, vacuuming your carpet, it needs to be able to see where things are to not bump into them. Or, throw itself down the stairs or whatever.
Yeah.
And some are better at that than others. But so for sensing, what the state of the art right now is what's called LiDAR, which is basically a system in which a bunch of lasers shoot out. And so the robot then uses that to create a sort of 3D map for itself of what's around it. And some of them complement this with cameras and things like that. But lasers are the basic part of that. And LiDAR was actually developed for a contest called the Grand DARPA Challenge.
That's DARPA, the procurement wing of the military we talked about.
I would assume
before.
so, yeah.
And so this just kind of goes to show how much those sorts of contests like Peter Diamandis' X Prize and things like that do really incentivize innovation. But regardless, in the 2004 Grand DARPA Challenge, which that challenge is basically just people racing robots in the desert. So one of the contestants, I think there were teams, but they developed LiDAR so that their robot wouldn't be running into rocks and things. And now that technology is used by many robots. It's also used in self-driving cars to sense things around it and so on. Another use for LiDAR is to be able to sense other things in the environment, like if you've got a robot that's helping pick apples or helping in other agricultural functions, it can pick up on certain subtleties, like if the apple is ripe or not.
Yeah.
In the future, they're hoping to use it to sense things that people can't see. So the example that I found was a robot going through a busy office building with a shiny floor and being able to see reflections of people coming around the corner, so it doesn't just go bolting out in front of people.
Yeah.
Dogs can't do that, so...
Well, and obviously where we are, we have the little delivery robots now driving around.
Right, and they just stop when something comes in front of them.
You can get really close to them before they make any effort to avoid you,
Yeah.
and then they suddenly jerk to a halt and turn and try and get around you. But then
Sometimes they just wait. Like,
they're
they'll
not
just
good
stop
at
away.
dealing with moving objects.
Yeah.
They very easily get around. I mean, I've seen them sit there waiting for a parked car to drive past them for so long.
Yeah, they're not amazing, but they're...
I mean, they kind of are amazing,
Well,
but they've got a long way to go still. Yeah.
They deliver food pretty close.
Yeah, they've always come. I had to rescue one from the end of the street when I ordered something once, but that just ran out of battery, I think.
But yeah, so that's one thing. And then the other thing is, how do they move? Besides wheels, obviously, most of them have actuators in them. So did you want to...
Yeah, so an actuator is a kind of a broad term. It's really any component in a machine that turns a signal into a physical movement, almost actualizes the movement is a way of remembering it. But in robotics, it tends to refer to a combination of gears and motors in a single unit that functions like a muscle. So you've got a jointed arm and it enables that to move. But it's about having that fluidity of movement, turning those signals into clear movements. But as I say, usually it refers to that, but it can also refer to other kinds of sort of robotic muscles, which can be hydraulic or compressed air operated, which is more akin to a human muscle, really, where you have that kind of expansion, contraction. But as I say, typically it's more just a motor and gear together that's designed to create that smoothness of motion. You don't want to you want that kind of fluidity.
Sure.
So that's where actuators come in.
Fantastic. And then people will often talk about robots as having artificial intelligence, but that's kind of a misleading term.
Yeah, I mean, and that has its origins in science fiction, doesn't it? And it's really is still science fiction, despite the fact it's become popular to refer to something different, which I think is what you're sort of...
Yeah, a lot of people call things AI when really what they mean is machine learning, which you'll talk about in a second, but there's also, when it comes to robots, typically what people are calling AI is machine learning or enhanced sensing or both. So I'm going to talk about the sensing part, and then you're going to talk about the machine learning part. But
yeah, I think even that term is a little problematic, but
we'll come to that.
Yeah.
So this enhanced sensing, for example, you have a private company called SynTouch that have developed fingertips for robots that can sense not just that something is there, but more about that something, specifically things like temperature and texture and stuff like that. So it's getting it closer to what a human could feel if it were to touch something.
Yeah.
And then at Columbia University, they're working on a project, I'm not turning British, a project using photodiodes. And so those fingertips of the robots are covered in silicon on the inside. They have what are called photodiodes, and photodiodes turn light into electric current. So the purpose of that in this case is to sense
Pressure.
Right.
So the more pressure, the more light is turned into electrical current. And
Okay.
so then the robot can tell exactly how hard you've poked it.
Yeah. Or how hard it's poked something.
Oh,
what the thing it's poking is.
Yeah,
You
yes.
see robots bent over just touching things, trying to figure out what they are. Yeah.
So you can see how that's helpful in getting the robots, up to speed with being able to interact with their environment. But the other component of that is machine learning.
Yeah, and machine learning, I won't get too much into the term itself because I'm writing a piece on this for the objective standard at the moment, specifically talking about ADAR, which is a robot that paints, and so I get into the problem. The very quick summary is that learning is the thing that conscious minds do, and what machines do isn't quite that. They integrate new information that they can detect
With their programming.
they detect through their sensors into their programming. So I think my colleague John suggested sort of self-programming as an alternative or something like that, which isn't quite right either, but
It's closer.
We don't really have a good alternative to the word learn, so we've just anthropomorphized it in those terms, but that is kind of what it is. It's not learning in the way that human beings learn, but it's adding to your programming through inputs, and that's a really cool thing. I really don't want to underplay that. It's just that we have to be careful about our use of terms with these things sometimes to avoid misconstruing what they are. But a good example of that is BRET, of progress in machine learning, and that stands for Berkeley Robot for the Elimination of Tedious Tasks, which is another of these wonderful names.
Get on board with this, yeah.
That you come up with, like Electro, the Moto Man. BRET is a laundry piling robot. It's intended, as the name suggests, to do all the boring stuff you don't want to do at home. It's very good at sorting your clothes into piles and putting them in baskets. It also taught itself how to do the triangle hole into circle.
Oh, that you have kids do, yeah.
Those games. It just trialed and errored its way through those, and then knew how to do it. I don't actually know if it would know how to do any of them now, or if it would just learn how to do the one it was given. But nevertheless, it was able to follow its programming to rule out certain routes and then find the solution.
I suspect it would be easier for it to do a new one, just based off of something I was reading about how you can train robots on rough terrain, and then they're better able to handle other terrain.
Yes, yeah, exactly.
I would imagine it works kind of like that.
That's it. The other thing I want to talk about is Google trained a robot dog called Go, named after the real dog, Laika, the Russian somewhat cruelly launched into space without any means of getting back in the 1960s or 1950s. But Go was trained in an interesting way. They motion captured a real dog. So motion capture, like if you've seen Lord of the Rings or Planet of the Apes, they have Andy Serkis covered in little dots that the computer then models his movement and then puts a computer generated character to do the same movement. So Gollum in Lord of the Rings or Caesar in Planet of the Apes is all of that. It's an actual performance by an actor that's captured by the computer. They did that with a dog, then used that to model a CGI dog, which then was copied over onto a CGI robot dog that had all the movement constraints of the real robot dog, and then that was used to program the real robot dog. The consequence of all that being that the real robot dog acted exactly like a real actual dog.
Did it chase its tail?
It even chased its tail, which it didn't have a tail. But it's very cute. And I'll come again on to another example later of how this just smooths out the process. If instead of you having to program the whole thing yourself, you can get it to mimic a real life form or something in the real world.
That's really cool. So we want to talk now about a couple other recent advancements. Those are things in recent decades we've been talking about. What about these last few months, even robotics? And let me just say, there's so much going on. Like, we had to really struggle to kind of narrow it down for this episode to what we wanted to focus on. But we've picked 4 that we think are particularly useful to focus on. So the first one is the most contrived acronym I've ever found, called Leonardo. So Leonardo stands for Legs Onboard Drone. You can see how they just picked the letters they wanted and dropped the rest, but whatever.
Or even the sentence doesn't really make sense.
No, Legs Onboard Drone, what?
So Leo was developed by the a team at the California Institute of Technology in Pasadena. It's a private university, led by a person named Soon Jo Chung. And the purpose of Leo, well, the basic concept of Leo, rather, is that he both walks on 2 legs and has propellers, so he can fly and walk.
Right. I'm trying to picture that, and I'm failing, but
I mean, it's not very
humanoid. It just has 2 legs, and then, like, where the arms would be, it has propellers instead.
Right, okay.
And so the purpose is that, I mean, it can fly or walk, but it can also...
mince things with its propeller arms.
No. It can, once it's up somewhere high that's hard for it to walk, it can use its propellers to stabilize itself.
Right.
So it can do things like skateboarding and slacklining that are hard for people to do even.
Right.
But the actual function of the robot is to do tasks in high areas, like checking on voltage lines and construction sites and bridges and things that are just hard for people to get to.
Yeah.
Chung says, in such applications, conventional biped robots have difficulties with reaching the site, and standard multi-rotor drones have an issue with stabilization in high disturbance environments. So the purpose is to fix, well, why don't we just use a drone? And why don't we just use a robot? We'll just put them together.
Yeah.
There's one issue at the moment that's preventing Leo from just being sent out into the world, which is its battery life. It only lasts about 3 to 5 minutes before it literally has to sit down to recharge.
His propellers are like one of those little handheld fans you get that just die on you. And
yeah, exactly. Yeah.
So hopefully the battery life issue can be fixed soon, but still a pretty cool advancement that's useful.
Awesome. So another one I picked up on was Amazon's new household robot, Astro. And so this is a, help you out at home, kind of like what the Honda P3 was intended to be, but it's there really to make sure your home's secure and monitor for safety and security purposes. It's been compared a bit to the Tesla bot. The difference is, firstly...
I was just going to ask what's the difference,
Yeah, firstly, well, Astro exists. It's not a dude in a suit. And
there's that.
And secondly, the Tesla bot is more intended for kind of high-risk activities, and Astro is really just sort of your home security bot. But Astro is not anthropomorphic. It's more like R2-D2 from Star Wars. It's like a little thing on wheels that drives around. It actually has a screen on it with sort of facial expressions. It's another way it can communicate with you. The cutest thing, which is very like R2-D2, is the fact it has a little periscope that can come out of it.
That is cute.
And you're doing the clapping thing. It's over-cuted you. But it can go over to the oven and zoom up its little periscope and look around and see if the gas is on and things like that, and peek through the window on your front door and make sure everything's safe and sound.
So does this raise any privacy concerns then?
Yeah, because Amazon with Alexa have had all these privacy issues, is Alexa working for the CSA, then they've designed it specifically to have off switches for its cameras and audio, although that obviously impedes its ability to do anything.
Right, it can't see
where
it's going.
And you can program it with out of bounds zones, so it can't go into certain rooms if you tell it not to. And they're also keen to say it's not just Electro on wheels. It's it's got a lot more capabilities than that.
Sure.
But yeah, no, it's I just love the image of the little I imagine if it gets buried in snow like R2D2 does at one point, it just pops the periscope out to look around. But no, I think it's really exciting.
It is really exciting. You said this is real too. Is it like on sale?
No, it's on sale. $999.99 US are. You don't use RRP in the US, but that's its initial retail price. Its actual retail price is $14.99.99, but they're doing it on sale for the initial.
So if you're moderately wealthy, this is within reach.
Yeah, this is not something I'm going to be buying anytime soon, but hopefully it's the precursor of something I might be able to buy in 5-10 years time.
Yeah. So on the subject of cute robots doing daily tasks, there are kitty robots, as in cats, in being trialed in Japan to deal with a shortage of waiters. So these are sort of like the Amazon robots you were just talking about, in that they have a screen for their face that has a variety of facial expressions, which really, to my mind, raises the question of what if you make your robot sad? How do you make your robot sad? Like, what are these facial expressions that it's been programmed with? But anyway, the robot, it's not very humanoid or even very cat-like. It's just got this screen on the top, and then in the middle it's got 4 places for putting food, and then it's just got like kind of a round base that it moves around on. So you just, the people in the kitchen put the food on there and tell it which table to go to, and it'll take it there.
Right.
It's pretty good at sensing obstacles and not running into people. And so they're testing it right now. They've got 2,000 of them at a restaurant chain called Skylark,
Cool.
where they're having issues with staffing. We're having the same issue in the US, but I think it's more chronic in Japan because they have like more of an aging population.
Mm-hmm. Yeah.
So that's one of the other reasons they wanted to bring it in too with COVID. That's less interaction between people, and so hopefully less of a chance for COVID to spread. But yeah, it's not taking jobs in any respect because we can't fill waitstaff jobs in the US or in Japan.
Yeah, I mean, also that's just not how economics works anyway. But we've seen. I mean, we talked a couple of weeks about autonomous trucks on this show, and now the UK has, and some other countries have severe HGV driver shortages. So
HGV?
Heavy ground vehicle.
We don't have that term.
Truck driver shortages. Where autonomous trucks would have been really handy to keep things running and keep everyone else in their work.
Yeah, it didn't actually have a fuel shortage. You had a shortage of fuel transportation.
Yeah.
But that's all I had on the kitty robots. They're not quite as cute as they sound, but they're still pretty cute.
I mean, everything in Japan is cute, really. But so I wanted to talk about the Trimble X7, which is effectively a sensor that a company called Trimble has mounted onto the Boston Dynamics Spot, the little dog bot that Boston Dynamics does. And the point of this is to speed up the monitoring of construction sites. So obviously construction sites are very rough and bumpy places where the robot dog can get around more easily than the human being can. But what the X7 does is it scans the environment and builds, I'll have to look at my notes, it builds a real-time composite point map. Which
composite, as we say in the US.
Yeah, so I think both our countries on different words have a tendency to mispronounce things. But real-time composite point map, did I say?
Yes.
Which is basically a 3D model of the construction site in real time that's fed back to the office, so that the staff in the office can look around a current accurate picture of what's going on the site. And this saves days and days.
Oh, I'm sure. A person going out to do that would take forever.
Of somebody,
even someone who's good at it.
Abseiling off the side of a building, or whatever, hanging on for dear life, trying to find all the little points of metal fatigue or misaligned bolts and all these sorts of issues that might come up, or just monitoring, how the site's going, taking pictures and things. And this thing's just building it as a navigable 3D environment that the staff in the office can instantly look at. So it's a good, interesting fusion of example of Spot in commercial use and being combined with somebody else's tech to really save a lot of time and speed up, and also make safer and hopefully not just safer for construction workers, but a better building at the end of the day as well. So you probably find issues that humans might just miss.
Yeah, so that's flows right into what we wanted to finish up with, which is just talking about all the ways that robots enhance human flourishing, since that's what we do on this show. And so one of the ones we've talked about is just protecting people by taking their place in dangerous environments. on construction sites, in rescue situations when there's been a building collapse or a natural disaster, cleaning up toxic waste, infectious diseases.
Yeah.
So on that last point, we talked about the die casting with the molten metal, things like that. On that last point, there's Tug the hospital robot, and monotonous tasks too, not just things that are dangerous, but things that we just don't want to keep
like
doing.
Brett.
Like Brett,
Yeah.
folding the laundry for you, or sorting the laundry. But yeah, so on that last point about reducing spread of infectious diseases and doing monotonous tasks, there's a hospital that has a robot called Tug.
Cool.
I don't know if that stands for anything. His name is just Tug. And Tug just delivers food and medicine to patients. It just trundles along into their room and brings it to them. There's a bit of a downside to Tug. He's not very good at getting around obstacles. He has to call for help.
So there's a trolley in the corridor. He just says, "Help! I can't get by."
I mean, it's a little bit more high tech than that, but not much.
Right.
Basically, there's a cart in the hallway, and he just pings back to the office and says help, and they navigate him around the cart from the office. So nobody has to go out to him.
Yeah.
But it's still, he still needs help. But they also help with science and stuff. And doing things better than we can.
Yeah, so I wanted to sort of talk about science broadly because, firstly, I talked earlier about space exploration and the ways in which, I was talking about space probes specifically, but now there's actually an opening avenue for robotics more specifically in spaceflight. One thing is just, I'm reading Robert Zubrin's book, The Case for Space at the moment, and he talks about Mars missions in that and saying how if we want to send humans to Mars, the best thing we can do is send automatic equipment ahead of them, send missions that are unpiloted that can land, set up the habitation for the human landers, make fuel on the surface of Mars, there's so many resources there, do all of that stuff, get the whole thing up and running before any humans arrive. So, having advanced infrastructure in place and everything running before anyone's even on the ground is a really good way to actually improve the human missions. Another thing is, talking about hazardous environments is, on the outside of the space station where you're in direct sunlight and there's no atmosphere or Van Allen belts to protect you and you're being bombarded with radiation all the time and you might fall off and go spinning into space. People hang out on, people do this, all EVA, extravehicular activity. All the time on the ISS, people just go outside and work on it, hanging on to these railings 300 miles above the ground. And
crazy stuff.
Yeah, so one thing that NASA's been looking into is, putting robots into that kind of role so they can do that maintenance on the outsides of spacecraft. And then there's a number of other fields. You've got the Ingenuity and its little helicopter on the surface of Mars at the moment, needing to be able to operate, like I said earlier, just so far away from Earth. Yeah. But there's also all those other places that you do science that are hard to reach, like you're saying, dangerous places. Volcanoes is an obvious example. The bottom of the ocean or undersea environments, super high pressure environments, just high temperature environments, deep in the desert, high latitudes. So there's all those kinds of situations as well. And then there's also the medical applications. You're talking about, bringing people medicines and stuff, but also actual surgery is one area where at the moment I think we're still really in a situation where you wouldn't want a robot potentially blundering somebody's surgery, but I think when we get robotics to a good enough point, you'll feel the other way where it's, I don't want some human working on me when I can have a machine do it.
Well, it's the same with driving cars, right? Right now they're not to the point where they're better, but there will definitely come a point where self-driving cars are 10, 20, 100 times safer than a human driver.
Yeah, it's a bit
the same way.
different with surgery because you have to be such an expert to be a surgeon, and I don't want to be disparaging about that at all. It's an incredible thing to be able to do, but I think you'll always need a human there with the robot.
But most surgeries, especially difficult ones, take 3 to 4 people.
Yeah.
So if you could get that down just in terms of labor and training to one person and one robot.
You can speed up some of those atrocious NHS waiting times maybe.
Mm-hmm.
But no, the other thing is I think you'll just need someone there to be able to respond to unexpected
emergency
situations.
Just for the safety of the
patient.
patient.
But the point is that robots are just that much more precise. They can know within the nanometer how what they're doing, how far to go, all that kind of stuff. So it can avoid those inherently human, no matter how well trained or how proficient you are, inherently human little errors that can happen here and there. There's also interesting potential, which we might talk about somewhere else another time, of nanorobotics, of just microengineering electrical components to go inside people's bodies help fight diseases, help heart rhythms get back on track, all that kind of stuff. And the more we're able to machine these things at a smaller and smaller scale, people already have things inside them that can achieve what was impossible 10, 20 years ago.
Right, yeah.
Yeah, definitely. So we want to wrap up on a fun note, though.
Yeah.
as
fun as surgery is.
As important as those things are for human flourishing, having fun and enjoying your life is also important for flourishing.
It's essential.
It's
There's
essential.
no point living if you can't have fun.
No, not at all.
So yeah, to that point, we wanted to talk a little bit about, I'm going to talk a little bit about robots in theme parks.
Cool.
So
I love theme parks.
So this is advanced even amazingly in my lifetime. I remember going to Disney World as a kid, and you'd be on these rides, and they'd have these little moving, they moved really jerkily, and just, it was clear it was a machine, but they had these little robots, and now they're so much more natural looking, so much more realistic when they have characters talking to you and things.
Yeah, I went to Tokyo Disney Sea a couple of years ago, and they have this ride where you're on a little boat going through this. It's actually inside, but you feel like you're in all these different towns and villages and landscapes. And
It's
each
a small
one
world.
is I think so. And each one is full of characters interacting, moving around. And you completely engross it, even though you know that as soon as you've gone by, it's gone back to where it started and it's about to do it again. But it's still all on a track, but it's convincing in a way.
Yeah. So Disney is on the forefront of doing cooler and cooler things with this. So I'll start with one that's cool and one that I don't like so much. So and the coolest one is what they call stuntronics. So you have stunt artists who can do crazy flips and jumps and leaps and things that are very dangerous. But there's still a limit, and you're putting somebody in danger when they're doing those things. So they've developed robots that can do, they've got one that they're putting in a Spider-Man suit, and that should be coming out soon, actually. They'll have Spider-Man in a performance kind of above your head, jumping around and doing what Spider-Man does.
Okay.
Can he swing on a web? No, yes he can. He's a robot. Yeah.
Yes, he can. He's a robot. Yeah, exactly.
And then there's one, and I'll link to it in the show notes, but it's really cool how to show the progression of what it's doing. So the stunt is jumping from somewhere high, doing a double flip, and then landing in a specific spot. And they start with a really simple, it's just a two-hinged thing that just kind of bends a little bit, and it gets more and more complex until it's a fully humanoid, this could be a character in a movie type robot.
You could get all of these stunt robots in a little group together and call it Cirque du Solenoid. No.
No, not doing that.
But yeah, so it goes from, it's just cool to see that progression in 2 minutes or something. It's a super short video. It took actually months in real life, but if not years. But then the other thing they're working on, one of the other things they're working on is kind of creepy, I think, because they're trying to develop robots that can interact with you the way a person interacts with you. So we're sitting here talking to each other.
Talking at each other.
Hopefully not. We're talking to each other, we're making faces at each other, we're responding to facial expressions. If you went over there, suddenly my eyes would go over there.
Yeah.
They're trying to make a robot do the same thing with really realistic eyes and facial expressions, and I just don't think I like that very much, actually.
No. It's you feel like you're talking to a fake face, don't you? Yeah. But then again, if you want to get to the sort of Data from Star Trek situation where it is like a human being, then
I guess you gotta do that, but
doing that prematurely when you know it's not anything like a human being on the inside is potential for some seriously creepy stuff. But
so we'll leave you to turn that over in your mind, and you're going to talk about robots in movies now, right?
Yeah, not exactly that, but the application of this technology to the film industry. So if you go way back to our second episode, I talked a bit about the Volume, which is the camera setup that they used on The Mandalorian and increasingly a number of other shows and films. I wouldn't be surprised if the new Dune movie is partly using that kind of tech, just from how fantastic
it looks amazing. It wouldn't surprise me, yeah.
But I don't know for sure, but certainly The Mandalorian did, and that's a situation where they're shooting in a virtual environment, but the virtual environment and the cameras are talking to each other, and they both know each other's positions, and all the lighting is responding in real time to all of that. So that's just one really interesting example of that kind of high-speed programming computation being used in film. Another one is sort of a similar situation to the dog we were talking about earlier, where they taught the robot dog to move based on how a real dog moves. they're doing this with CGI characters in films, particularly for facial expressions. Instead of getting some poor visual effects artist, the guy who had to remake Sonic in 6 months, to design, exactly what eyebrow moves in what point, and frame by frame, they show it footage of. It's kind of like deep faking. It's they're showing it footage of somebody who's doing those expressions, and it's copying them and building into its programming based on all these different samples.
Save a lot of time, I imagine.
Yeah, so it massively saves time on movies that are spending $80 million employing 75 different effects houses to watch the end of movies, and there's just like this endless stream of credits.
Yeah.
And if you can cut down on that and get algorithms to do some of that work, then I think that's a really positive thing.
Absolutely, yeah.
And then the other thing is, overlapping with what you're talking about in the theme parks is animatronics. And as good as CGI gets, everyone prefers a physical object. If you can do it, you should do it. CGI should be a tool to replace that when you can't. But if the best looking scenes in Jurassic Park aren't actually really the CG scenes. They're those gigantic T-Rex animatronic they built, and getting those to move more believably. If they can move and interact the way you want them to, if you want dinosaurs or robots or aliens or things like that in your films, then that's also an interesting direction for things to go in, and that's smoothed out a lot in the last few years as well, because that technology has improved. The problem they had on Jurassic Park was because they had rain in that T-Rex attack scene, it weighed down the thing and it couldn't move properly. After a few minutes it started juddering. So more modern technology, maybe that wouldn't have been such a problem.
Sure.
Yeah, well, that's all we have for today. So thank you so much for joining us on this slightly longer than normal episode. We hope you enjoyed it. Just to recap what we talked about, we covered robots, the history of robotics, all the way back to the Egyptian water clocks hitting a gong, up through Nikola Tesla's radio-controlled boats, Electro the Moto Man we talked about, the Unimate arm, up through Shaky, the early deep space probes, up through robots like Wabbit and Famulus, who were, more precise and able to do more things, up through Asimo and Boston Dynamics dogs, the P3 from Honda. And then we talked a little bit about how do robots actually work? How do they sense things around? How do they move? And the machine learning that people are developing to get them to do more things and do things better.
Yeah, and then onto that, after we were onto new advancements, we had the Kitty robots in Japan, which was the other one I did, the Amazon robot, and then what was your other one?
Oh yes, I talked about Leonardo, who's the drone,
the terrible
bipedal robot.
The terrible acronym. Yep. And then I had Trimble's construction site.
Mm-hmm. And we just finished off by talking about applications more broadly, everything from replacing humans in dangerous situations to helping us do science better in space and do surgery better, do medicine better, and then more fun things like theme parks and movies. So,
cool.
Thank you so much. You guys have a great day. We'll see you next time on Innovation Celebration.
Thank you.